So in the previous video about metals, we focused on metallic bonding, and looking at the atomic structure of metals, we found that the electrons on the atoms in metal elements aren't localized to specific ions or atoms. They're actually free to move around the metal structure. And the word that we used to describe that was that the electrons were delocalized. There was a sea of delocalized electrons surrounding an array of positive nuclei. And that really explained the electrical conductive properties of metals, why metals are really good conductors of electricity, because current can move through this sea of delocalized electrons because those electrons are free to move. We now want to look a little bit further at reactions of metals by considering what substances we can react them with, and not just the fact that they conduct electricity. So to do that, we're going to be basing all of this off of the reactivity series. Now all this is a list of most of the metals from the main groups of the periodic table, and they are listed in order of their reactivity. So starting at the most reactive, going down to the least reactive. So they're in reactivity order, which is why it's called the reactivity series. And what we're going to do is we're going to see how each of these elements, each of these metals, will react with one of three possibilities: oxygen, water, and dilute acids. And we're going to consider the equations that are formed and the products that are formed in each case, if they do indeed react. So we need to know three sets of reactions here. The first one is going to be metals plus oxygen. So when I react a metal with oxygen, usually from the air, I form a metal oxide. And as an example, we can have magnesium solid reacting with oxygen as a gas, forming magnesium oxide. And we can actually see this by looking simply just at a strip of magnesium ribbon, which is this thin magnesium metal. So what's interesting is, if we look very closely at a section of this magnesium ribbon, we can see that unlike a property we might associate with metals, that is that metals are usually quite shiny, this magnesium is quite dull. And why that is because the surface atoms on this strip of magnesium, the ones that are on this very top layer of metal, have reacted with oxygen in the air and have formed this coating of what is basically magnesium oxide. So if we take this magnesium strip, this strip of magnesium ribbon, and we scrape away at some of that outer layer, and here I'm just using the sharp side of a pair of scissors, because this metal is also quite soft, so this is quite easy to do. And I keep scraping away at that top layer and file off some of that coating, I should find that the metal underneath, compared to the rest of the strip of magnesium, is actually quite shiny. And that is because I've removed that outer layer, which is metal oxide, magnesium oxide, and I've exposed the unreacted magnesium metal underneath. So that demonstrates that it was in fact oxygen that this metal has reacted with from the air, because the atoms that were underneath that layer remain unreacted. And if I leave this sitting out for a few hours, we'll find that it returns to look like the other side, this sort of dark, dull coating of magnesium oxide. So that is our first set of reactions. Metal plus oxygen gives me metal oxide. Now if I look at my reactivity series, I will find that in reacting with oxygen, I go right from the top of the table all the way down to copper. So most of the metals in this reactivity series will actually react with oxygen. So now we want to consider the second one. What about water? How many react with water? So when metals do react with water, they form a metal hydroxide, and they also form hydrogen gas. So some metals will do this. Some metals are so reactive in water, in fact, that they have to be stored under oil to prevent any moisture getting in contact with the surface of the metal. So a bit like my magnesium ribbon, some metals are so reactive that they will absorb the moisture from the air. And that can be quite dangerous. These metals are really reactive and can also be explosive if exposed to enough water. So, for example, potassium, as a solid, will react with water in this way, and so has to be stored under oil. But when it does react with water, it forms this metal hydroxide, this potassium hydroxide, and hydrogen gas. So if we were to add that to our reactivity series, we would find that compared with oxygen, not as many metals in our table react with water. That's because it's only the most reactive metal elements in the series that will do this. So think of water almost as the weakest thing to react with, so it's actually quite difficult to get that reaction. So it requires the metals like potassium, sodium, lithium and calcium to be very reactive to make this reaction happen. Whereas the one with oxygen is a bit easier. So more metals will do it, even if they are not very reactive, like copper, for example. But what about the final reactant? What about acid or dilute acid, which just means not very concentrated acid? Well, when metals react with acid, they will form a salt, and they'll also form hydrogen gas, just like reacting with water. That is because, again, we are adding hydrogen into the reaction. So, for example, if I go back to magnesium solid, magnesium will also react with acid as well as oxygen. We'll find that we produce magnesium chloride as our salt, and notice that I've balanced that equation to factor in the 2 chloride ions here, and I'll also get that hydrogen gas that I mentioned. So finally, adding that to our reactivity series, we will find that relative to oxygen and water, we actually have more elements in our reactivity series reacting with the dilute acid. And you can think of that as being because the acid is more reactive than the water, if you like. So it's easier to get these sort of middle league elements to react with the acid. So if you have to think of a pecking order here, remember that oxygen is the easiest to react with our metals, so most will react with oxygen apart from these very unreactive metals down the bottom. Then, using something quite strong, quite concentrated, like